Okay, AT Finite, welcome to day 3 of our unit on cryptography. Today is, of course, the online learning day, right before spring break. Mr. Zatur and I decided to kind of cut this lesson a little bit short because we weren't really quite sure how to fill this third day anyway, and with the online learning thing, it was kind of like, you know what, let's just do what makes sense. So this might seem kind of light, but we're kind of doing that on purpose. Okay, and remember, there's always the projects. If you feel like your AT finite life is a little too finite, there's always that you can be working on. Okay, so this is from the TCMS book, and these are some worksheets that come from the same source as that Hill worksheet we did, the Hill cipher worksheet we did not too long ago. So that might be why this looks familiar. Anyway, it's a little bit more of a deeper investigation into modular arithmetic and Z sub n, like it says at the top. So this is worksheets that go along with problem 10 and 11 in the book that you already probably have the scans for, I think. All right, so here we go. Every non-zero real number has a multiplicative inverse. Just take the reciprocal of the number. So that's talking about in regular real number terms. You're used to any number in the regular number line number system that you've been used to your whole life. To find a multiplicative inverse of that, all you do is take the reciprocal, and those two things will multiply and make 1. For example, you could take, 3/4 times 4/3, it equals 1. And why is that important? Well, 1 is the multiplicative identity. So multiplying, so imagine you had some number or some piece of like a plain text message, and if you kind of transpose that or manipulate it or modify that by multiplying it by one thing, we need to know what is it that we multiplied to kind of undo that. And that's why this is a big deal. So in the end, by multiplying by both these things, we get back to what it would be like to not really multiply it by anything at all. So that's the significance of inverses in general. Do you think every number in Zn has a multiplicative inverse? Well, that's kind of a complicated question, actually, and you'll see why. So consider Z sub 7. So this is where we mod everything down mod 7. The elements of Z7 are the elements 0 through 6. That might be helpful to kind of remember. These are the elements we're talking about. I feel like I've been online all day because I have been online all day. Okay, find a number in Z7 that you can multiply by 3 to get 1 mod 7. In other words, and we did a little bit of this last time when we were talking about the decimation cipher, but we just kind of did one example and moved on. This is going to be, like I said, more of a deeper investigation. So is there something you can take 3 times something that equals 1 mod 7? Well, think of the numbers that are going to be congruent to 1 mod 7. Those numbers are, if I draw this, hopefully that makes sense. The numbers that are congruent to 1 mod 7, of course, are 1. The next number that's 1 when you mod 7, in other words, when you divide it by 7 and think about the reciprocal, the next number would be 8. I'm just adding 7s here, 15, 22, etc. All of these have a remainder of 1 when I divide by 7, and this goes on forever, of course. Well, is there anything that's another member of this set that I could multiply here that would end up being 1? Well, sure, I could get 15 if I multiplied this by 5, and that's what that's about. Same thing with 2. 2, what could I multiply it by to make it equal 1 mod 7? I'd have to look for something in this list up here, and usually the smallest one, well, always the smallest one is going to be the one where I find the number that is going to be from this small set of numbers. So 8 is the target there, and I'll get there if I multiply by 4. Find the multiplicative inverse of 6. Same thing, 6 times, I need to find one of these that's a multiple of 6. Now I got a little farther this time. I think I'd only have to look for about 7 of these numbers before I find it. After 29, the next one would be 30. Adding another multiple of 7, so I'm writing and talking at the same time, is also going to be 6, because 6 times 6 is 1 more than a multiple of 7. Okay, I don't think we've done this before. This thing is called a Cayley table. Cayley tables are awesome. So this is, we're going to write out the times tables for everything in Z10. Z10 is a little different. You'll see why. It's going to operate a little bit different than mod 7. I think the inverses we did in class last time, I gave you the table for or for Z11, or for Z, it was 15 or something, and we did 11. And though I never really explained why I picked the numbers that I picked. Z10 is, in general, it kind of depends which number you pick, how this is going to kind of look and how things work out. Anyway, so they picked Z10 here to show you something very specific. And we're going to do our multiplication tables in Z10. So for each number in Z10, try to find its multiplicative inverse. Okay. So like I said, the first thing you're supposed to do is just fill out this Cayley table for multiplication for mod 10. So this is simply like the entire times table for all the members of mod 10 times all the members of mod 10. So let's get started. I won't make you watch me do the whole thing. I'll find patterns and I'll skip ahead, I promise. 0 times 0 is, of course, 0. 0 times 1 is 1. This is, whoa, that's not true. 0 times 0, 1 is 0. 0 times, etc. And, let me just do this as I get to it. And down this side, 1 times 0 is 0. 2 times 0 is 0, etc. Okay, that's not so bad. 1 times 1, 1 times 2. You thought this was a college level course, I bet. Yeah, right? Let me keep doing those. Okay, it's about to start getting interesting, I promise. 2 times 2 is 4. 6, 8. Okay, fine. I can't write a 10 here, but 10 mod 10 is, of course, 0. And it kind of feels like things around this part are going to start to repeat. Okay, so 2 times 9 is 18, but of course I don't write 18. So this is a kind of an easy one because we're really just thinking about the ones digit in all of these. Okay, let me repeat that one for you. And we can continue, and it's going to start getting kind of interesting each time a little bit sooner. So I'm just really counting up by threes here. 8, oh, I've got to loop around. 1, 4, 7, and of course it's the same on the next on the column. 4 times 4 is 16. 4 times 5 is 20. Feels like I'm counting up by fours, but I loop around every time I get to a multiple of 10 again. As I did that, I realized this is kind of silly. Sorry. Let me fix those. Okay. And multiply by 5. Look at the rows of 5 and the column of 5. That's kind of interesting. 6 times 6 is 36. And I keep going. Okay, and there we go. We've completed our first Cayley table of the year. And notice it's symmetrical along the diagonal because multiplication is commutative and all that kind of stuff, so that's great. And we're looking for inverses, right? So it says for each number in Z10, try to find its inverse. Well, wait a second. There's not a whole lot of ones in this table, right? When I'm looking for inverses, I'm looking for oops, that's not a good color. When things multiply to 1 is when I know they're inverse of each other. So there's a 1 there, there's a 1 here, and of course there'll be 1 there. There's a 1 here, and that's about it, isn't that? Yeah, that's it. So I've only got inverses if you're a 1, a 3, a 7, or a 10. Or sorry, 9. So what's going on here? So first of all, it says state any patterns that you see concerning which non-zero numbers in Z10 do not have an inverse. Well, it's not really surprising that 0 doesn't have an inverse because you multiply things by 0. It's kind of, that's the only number that doesn't have a multiplicative inverse in the regular numbers anyway. So because it's got its own kind of special property with multiplication. So that's not terribly surprising. But there's no multiplicative inverse for 2. And there's no multiplicative inverse for 4 or 5 or 6 or 8. The only ones that have multiplicative inverses are 1, 3, 7, and 9. And how do those numbers compare to 10? Well, if you think about what we've excluded here, we kind of got a preview of this when we were talking about what had inverses in Z, I think it was 26 when we did decimation cipher. Remember, we could only use numbers that were odd and not 13. Same kind of thing here. Notice what's got inverses here. Everything that has an inverse here is odd, and it's also not 5. All the even numbers and 5 share a factor with 10. So if anything's going to be divisible by 5 as it gets multiplied up the number line, it's going to share a factor with 10. Or I guess the other way, multiply something by 10, it's going to also be divisible by 5, or it's going to share some factors with 5 anyway. Same thing with all the even numbers because they share a factor with 10 also. So I mean, if you don't believe me, look in the table. There's no ones anywhere else. You're never going to loop around and find a 1 when you multiply stuff by any even number or 5. Never becomes 1 more than a multiple of 10. It's either a multiple of 10 or it's kind of an even. Notice the numbers in those rows. It's an even number greater than 10 or it's 5 greater than 10. They just kind of like are all on the same team that way. They never get around to 1s or 3s or 7s or 9s, interestingly enough. Anyway, what's the name for that? Numbers that share a factor for 10. Another name for that is, and I'll just type it in, we would say those numbers are not relatively prime. So the flip side of that is state any patterns you see for numbers that do have multiplicative inverse. Those numbers, 1, 3, 7, and 9, are relatively prime with 10. They have no factors in common. And you might as well say prime. If you're checking for this, it's easier to just check for whether or not they have prime factors in common. All right, for each number in Z9, try to find its multiplicative inverse. Okay, so we know what not to check, right? Like we're not going to check 3. We're not going to check 0. We're not going to check 3. And I guess that's the only things that have shared factors with 9. Oh, sorry, 6 has a shared factor with 9 because it also has a factor of 3. But let's try it here. So 1 times 1 is 1. So that's always the case. Did you notice that 8 times 8 is always going to work too? I think we talked about that the other day. Notice 8 times 8 is 64. That's 1 more than a multiple of 9. So 1 is the inverse of itself. 8 is the inverse of itself. What about 2? Well, we need 2 to multiply to something to be 1 more than multiple of 9. That would work if we did 5. So of course that works the other way. 5 times 2. I don't know if I'm going to fit these in order the correct way. We'll see. 3 I know isn't going to work because it shares a factor with 9. 4? 4 ought to work. Can I get 4 to multiply to be 1 bigger than a multiple of 9? So 10 or 19 doesn't work. Or 28. Oh, look at that. 28, 7. So by the same token, 7 times 4. So they're kind of multiples of each other. Oops. 4s are not strong with me today. It'll be 1. Okay, and then is that all of them? 6 we already talked about. Not going to work. And that's everything. So 1 is an inverse of itself. 2 is an inverse of 5. 4 is an inverse of 7. And 8 is an inverse of itself. Set any patterns that you see concerning which numbers in Z9 have multiplicative inverse. Well, I kind of already said that. The ones that do have multiplicative inverse are any number that does not share a factor with 9. Of course, 0 never does. So we'd only be talking about the numbers 1 through 8 anyway. And yeah, I think that's all we really have to say. Numbers that share a factor with 9 are not gonna work. And does every number in Zn have a multiplicative inverse? Okay, it kind of seems like, and we've talked about this a little bit before, 1 times 1 is always going to equal 1 mod n because it's 1 more than a multiple of n, just kind of by definition of being 1, right? So when I divide 1 by n, the remainder is going to be 1. And then the other one we found out last time was if you take n minus 1 times n minus 1, that's always going to be congruent to 1 mod n because this thing turns into, of course, n squared minus 2n plus 1. And this thing, if you were to mod this, if you were to divide this by n, that would turn out to be 0 mod n. So the whole thing is going to turn out I mean, by definition, then kind of, by looking at this is 1 more than that multiple of n, right? Because this is n times, I should write this. This is n times n minus 2 plus 1. So that's a multiple of n plus 1. So I know this is 1 more than multiple of n. It's kind of a cool little reasoning there. And then everything else, I guess it's just all we can really say, all we've really discovered here is and all numbers that are relatively prime with n. And so there you go. I thought about that a little more when I typed it out. Of course, we're talking about less than n minus 1 because n minus 1 is the greatest number in the Zn system. All numbers that are relatively prime with n. In other words, that means they do not share prime factors. Okay, now on to number 11. See if I can get this done in a minute and a half. You discover that not all numbers in a given modular have a multiplicative inverse. So think about when they do exist. Make some conjectures about which numbers have inverses, either in general or particular values of n. And it's asking you to do some kind of self-exploration or exploration in groups on this. This is kind of hard to do in a video. We will do this in class when we meet together, and so that'll be the value in that. Well, let's talk about B, at least. When n is blank, then every non-zero integer in n has a multiplicative inverse. For every non-zero integer in the system from 1 to n minus 1, we're saying that every single one of those has a multiplicative inverse. And that goes all the way up to, n minus 1. If all these are supposed to be relatively prime with n, if they share no common factors, the only way that's going to happen if n is prime itself. So that's kind of an interesting little factoid. Impress your friends at math parties. Okay, in Z sub n, how must m and n be related for m not to have multiplicative inverse? M has to share some factors with n. So in other words, m and n would not be relatively prime. Complete this statement. M has a multiplicative inverse in n if and only if, well, I think I just said this. So I hope that's been beaten into your head enough, the way they've asked this so many times, pretty much the same way. Or sorry, the same question so many different ways. I guess I should say other than one. Okay, great. I'll see you online. This video is here for your reference. Goodbye.